Thank you everyone for coming. I am Matthew Romano, and today I will be defending my thesis on planning, control, and estimation for diverse multi-UAS missions. I'm a PhD candidate in robotics, the robotics department now, and I am in the Autonomous Aerospace Systems Laboratory, directed by Ella Atkins, who is the chair of my committee, and professors Fazeli, Panagu, and Roscofter are additionally on my committee. So thank you all for coming. Unmanned aircraft systems, or UAS, are being used for a variety of single vehicle missions. This includes surveillance, inspection, and payload delivery. However, we can use teams of multiple UAS to perform these same missions, potentially faster, better, cheaper, more efficiently, and we can even pursue novel cooperative missions that we couldn't even with single vehicles. However, this comes at the cost of requiring team-wide coordination and working towards a common goal. The three missions that I'm focusing on in my dissertation are UAS traffic management, payload delivery, and wildfire detection. From these three missions, I'm focusing on four specific problems. For UAS traffic management, formation flying is a useful tool, so I'm focusing on formation control and formation planning, and then as well, payload delivery and wildfire detection, which I'll describe further. For formation flying, and in UAS traffic management, the goal is to have many vehicles fly in a shared airspace and coordinate their flight such that they avoid collision and things work out nicely. Formation flying is a potential solution such that the traffic management system only sees the formation as one entity and only plans for that, while the formation itself handles its own coordination. Within formation control, there's many techniques that can be used. Continuum deformation is one of them, which is a distributed and deformable method. However, prior to this dissertation, it has only been shown in theory and simulation. So the very first problem statement is to experimentally validate this, as well as address certain practical challenges in communication and control. On the formation planning side, sure, if we have this nice deformable formation that we can control and maintain a formation, it's useful, but how do we actually plan for this formation through space, deforming and all these things through space? And so in 6, there's been some initial work showing that it can be planned between preset waypoints, but it lacks a more general planner. So problem statement number 4 is to have a general deformable formation path planner. And this will work in conjunction with having an online guidance scheme to handle pop-up obstacles and failed vehicles for collision avoidance. Within payload delivery, if you have a single vehicle, you can carry a reasonably heavy object. Typically, you see this with military vehicles and other where you have a single slung load, but you have problems such as swinging and spinning. And if you use multiple vehicles, not only can you carry a heavier load, but you can potentially damp out some of those unwanted dynamics by pulling in multiple directions. Existing work for the multi-vehicle slung load problem assumes guidance is either pre-planned or piloted. But for environments that are either dynamic, cluttered, or unknown, this may not work. Consider a disaster relief scenario where you previously had satellite data, LiDAR point clouds, something of that nature, and then all of a sudden a disaster occurs. After that, you no longer have accurate data. You have to rely on onboard sensing. If your onboard sensing isn't perfect, you're going to have to go into a risky environment. In 9, they proposed, hey, if we have a user on the ground that can physically see the area, but doesn't know how to interact with the system, what if they simply push on the payload to have it move in the direction you want it to go? And so the idea is there's an intuitive interface that you don't have to train anybody a priori. You just say, hey, push on it exactly where you want it to go. And they showed that it can work theoretically, but use simplified user interaction, sensors, and state estimation. So problem statement number 2 is to actually realize this haptic guidance scheme experimentally with a team of UAS to direct a common payload. So have a user direct a common. And then lastly, the wildfire detection problem is dealing with, okay, so everybody knows that, in California, in the West, and in recent years, there's been significant wildfires that have harmed many people, property, and it's quite dangerous. However, using teams of UAS, fixed-wing UAS in this particular situation, we can potentially gather very useful real-time fire data and relay that to emergency response teams to help with their fire response and coordination. So the idea is we need to have these Vehicles fly in complex 3D terrain while avoiding fires and report accurate data to get an estimate of fire boundaries and send that to emergency response teams. This is a very complex planning problem, and the existing tools are just too slow for online planning, and they are more suitable for offline planning. This is due to whenever you have significant computational constraints, you really can't handle this dynamic, when the fire boundaries are evolving, things of that nature, real-time planning. And so there's a need for an integrating planning approach that can do safe, computationally efficient trajectories in real time for TMWS to find and map wildfires. And that's the third problem statement. Okay, so that was all the problem statements. And now I'm going to share the research approach to address each of those problems. For my research, experimental validation and testing has actually been at the core of it. And so in chapter 2, I describe all the infrastructure necessary to do this. So with a custom Quadrotor design, custom instrumented payload, as well as all the infrastructure to support this multi-vehicle flight testing. In chapter 3, I focus on the formation control problem and have guaranteed safety for a deformable UAS formation by extending a theoretical safety bound and combining it with a local controller error that we can actually obtain such that we can validate trajectories experimentally. In chapter 4, it's on the multi-vehicle slung load haptic guidance. And the approach is to use online user force estimation via inline tension sensors and combine this with haptic guidance with admittance control. And additionally, do all this with a real user experiment to show that it will actually work in practice. Approach number 3 is on the multi-UAS wildfire mapping. And what we did is we used the state machine to do task planning to allocate UAS between exploration and boundary following modes. And we achieved computational efficiency by separating a 3D planning problem into a 2D lateral and 1D terrain avoidance problem. Lastly, in research approach number 4, it's on the deformable formation path planning. Now, this is a proposal of a new global planner that can plan for these deformable formations through space such that they can not only translate, but translate, rotate, scale, and shear throughout space. And this is achieved by defining efficient interagent and formation obstacle collision check. Lastly, this is coupled with a low-level guidance via fluid flow navigation fields to avoid pop-up obstacles. Contributions from this dissertation include open source contributions, a M330 Quadrotor and associated flight controller that's all set up to have low latency motion capture feedback with multiple vehicles, the very first experimental evaluation of continuum deformation, an instrumented payload that supported the multi-vehicle slung load project that can additionally be used for educational and other research purposes, and the deformable formation planning via simulation and experimental validation. Innovations include an inter-vehicle separation constraint that's defined for that formation control work, such that we can guarantee safety using experimental bounds. This idea of a heads-up haptic pushing interface such that a user can move a heavy load through cluttered and crowded environments paired by multiple UAS. Multi-UAS path planning that's efficient such that we can support wildfire mapping over a large area to acquire that boundary estimation. And lastly, this hypercontrolled deformable formation path planner. So that was the introduction of the dissertation. Today, I will only be focusing on the infrastructure in chapter 2, the haptic guidance in chapter 4, and the deformation path planning in chapter 6. So for infrastructure, here is the M330 Quadrotor. It's a relatively low mass at about 1 kilogram, and most importantly, it's only about $300. So this is very important in educational situations as well as research when you need multiple vehicles and you don't want to spend $5,000 for each. And this is achieved by using off-the-shelf components. So you see there's brushless DC motors, nylon propellers, all these kind of standard components for a vehicle. And what's a little bit non-standard are these custom 3D printed propeller guards. So if you notice, they completely cover the propeller such that if two vehicles collide, which is in the research has been one of the goals to get them as close as possible to be safe, and sometimes they do collide. Instead of having propellers hit each other, we'll have the propeller guards hit each other and they'll simply bump off like bumper cars. That's worked fairly effectively. And that's also the most likely part to break, so that if it does break, we're able to 3D print it. And then the other thing that is a little bit different than a standard vehicle is the Beagle Bundle. So that's a full Linux computer So it's not just a microcontroller. We actually have, we can actually run whatever we want on there. And it has very nice robotics peripherals. A lot of us may have known it from the Rob 550 courses and whatnot here. And it's running RC Pilot A2Sys, which is another custom flight controller that we adapted from another project. So RC Pilot A2Sys, it's open source. It's simple. It only has about 12 .c and .h files, such that people that have never have a basic understanding of C programming can pick it up and get used to it. And it does this by relying on the Robot Control Library, which handles a lot of the low-level things such as filtering, input-output threads, timing. And it supports the basic flight modes necessary to do the research. So this includes autonomous trajectory tracking, via motion capture feedback. Set points can be commanded either a priori via trajectory files or in real time with navlink over Wi-Fi. And so here's just an example to show from the very input to the output. So we have complete control over every aspect of this. We can log every signal and change everything that we want. So this, as a researcher, this is a really nice tool to say, hey, I like how this is working, or hey, I know that something over there is causing issues, let's just replace it, or replace the entire thing with some complicated nonlinear. But it's proved very useful. And then about motion capture. So for our work, we wanted to focus on control, guidance, and high-level problems. And motion capture allows us to solve the state estimation problem. It allows us to have millimeter-level accuracy of vehicles, and the goal is to be able to have those be instantly available to the vehicles. But that's not necessarily true. We have to actually stream this data from the motion capture system to the vehicles. And so in order to achieve low latency feedback for 6 bodies, we had to do some testing. So we started off using just Wi-Fi, using the existing clients that come with all of these motion capture systems, and we sent data, perhaps naively, and we received about 100 to 400 milliseconds of latency, which for a fast-moving feedback control system may not work super well. And then we tried using wireless serial modules, XPs, and we were able to get data consistently at 40 milliseconds. Now, how do we actually test this? Well, we took the vehicle, which has an onboard IMU, which can estimate its own roll and pitch, which is fairly accurate, and the motion capture can also estimate its own roll and pitch. So we did a very careful prescribed roll motion, and then we compared the signals from both the roll of the onboard IMU and the roll of the motion capture, and we compared it, and this is the results. So the idea is XPs work very well. Potentially Wi-Fi could work if we mess with settings, who knows, but XPs works, and so we went with that. And then how did we get all 6 to send data at the same time without interference? Well, we had this Spiegel and Black interface with the existing motion capture system and send these serial packets. So if you notice, we're sending yaw, X, Y, and Z. So that's 4 degrees of freedom, when we generally at 6 degrees of freedom, including roll and pitch, but we trusted that the onboard IMU was sufficient. Sent it using some error checking, and we separated the commands, the data, into 2 channels, such that they don't interfere, as well as 3 time slots. And what we achieved was 6 bodies that we could send real-time data to effectively. This results theoretically in 100 hertz data rate, and we achieved about 60 hertz interference. And lastly, I want to talk about the instrumented payload that was custom built to support this research. You can see that it's made out of a styrofoam ball that was hollowed out. It's also right up on stage right here. And there's channels such that we can tie tethers and include electronics on the inside. It allows us to estimate user-applied force, compute payload guidance, and command quadrotor trajectories all in real time. Here you can see another look of it. The electronics are on the inside, so we have another BeagleBone Blue that's powered by a battery, receiving motion capture data over XP. Then it's connected to 2 PCBs that are each receiving load cell tension sensor data, as well as a push force tension sensor data, all with analog to digital converters to receive that. And this is how it fits into the larger system. So you can see the payload is at the center of the left. When a user pushes on to the payload can sense and send out commands to each of the vehicles over Wi-Fi. The vehicles then control to move in the direction of user applied force. The left side is all in real time on embedded hardware, and on the right side supports via the motion capture, as well as some high level telemetry and commands via the GCS operator. And we have a safety pilot that can act if anything happens. So next I'll talk about the slung load with haptic guidance chapter 4. So the idea is we want to be able to have the user push, have it move. So we want to actually be able to implement this and evaluate this in real life, such that it can estimate user applied force, update guidance, and then minimize payload trajectory tracking error in that direction. So in terms of external force estimation, there's lots of work on this. I'm grouping the existing methods into two categories. So one, what I'm calling resultant and low-pass filter on the left, where you have sensors that can measure all the forces of interest except that disturbance force that you want to measure. Then you use Newton's second law, you rearrange it such that you can solve for that missing force, apply a low-pass filter, and get the correct data. So in 11, you can see there's a humanoid robot where a graduate student had a lovely time just picking it to apply force, and they were able to estimate it using that low-pass filter. And 12 is focused on the cooperative payload project as well, where they use an averaging filter to do it to obtain that user input force applying it. Indirectly sensing the force can also be done. It's a little bit more complicated. In 13, they used an IDA PBC approach, where they had positions, attitudes, and derivatives, and then had a model of their system such that they could compute what the forces sensed were. Additionally, in 14, focused on the load transport problem, they used an augmented state extended Kalman filter to estimate that external force. And if you notice, there's these follower vehicles and leader vehicles. And what they did is the followers were estimating those forces and following along, and somebody was commanding those leaders. For us, we don't want to have to rely on effective models that may not be accurate. We're assuming that our payloads may change. We're assuming there might be lots of uncertainty. So we're going with the methods on the left, so variation. In terms of haptic guidance, specifically for multirotors with slung loads, there are two examples besides mine because it's a very niche topic. So 14 again, so what they're doing is they're using an admittance controller. They have a leader vehicle that's pulling on a payload. The payload then pulls on the vehicle, the follower vehicle then estimates that force and has that force update these virtual dynamics. So there's a virtual mass, damping coefficient, and spring constant. For their actual work, they did not have that spring constant, so just a mass damper. So basically, you can pull on the vehicle and it will move along. Additionally, in 12, there's what I'm calling an ad hoc admittance controller, where the user force was estimated in the direction of user force was taken as that theta 0, and then every iteration, it moved by delta r. So there was a pre-specified velocity discretely and a pre-specified and then you estimate that velocity. So it has no virtual mass or anything, so it just directly translates to that velocity. And so what we wanted to do is we wanted to take that formalism of admittance control and apply it to the cooperative payload project, where we're truly just pushing on the payload itself. So running the admittance controller on the payload itself as opposed to one of the vehicles. Here's a control block diagram of our system. If you look at the top right, we have the payload dynamics. You have 5 vehicles that are all tethered to the payload. They're pulling, so applying a force and potentially torques, and you have a user applying force as well. Motion capture system can sense positions and attitudes for all the bodies, and our user force estimation relies on inline tension sensors to obtain a force estimate. Payload guidance relies on admittance control to provide a set point for the payload controller, using motion capture command set points to all the vehicles such that they actually move the payload in the direction of user applied force. Here's our dynamics model. You can see that we have I vehicles. So each vehicle has body frame I, ground frame G, and payload frame P. We have gravity, drag, tether forces, and thrust acting on the vehicles, as well as torques from the propellers. The tether is on the center of mass of the vehicle such that no external torque is applied. The payload experiences similar forces, gravity, drag, tether forces, and additionally the user force. And these tether forces can additionally apply torques because they're not on the center of mass. Lastly, we assumed a spring damper tether model for the tethers with damping coefficient B and spring constant K. For user force estimation, we took these dynamics in the ground frame and we made some simplification. So we have the net forces equal to the mass times acceleration here. If we assume that we're quasi-static, which means our acceleration is near 0, we can set that away. And if we assume the aerodynamic drag is low enough, we can also ignore that as well. We reduce it to this simplified system. apply a low-pass filter, and use an offset term such that we can account for unmodeled biases and errors in real time. This F0 is set from the ground control station such that right before the user can approach the system, we can zero it out such that all the applied force, what the user is applying to the system as opposed to errors in the system. For payload guidance, we use admittance control. So you can see this is our virtual dynamics. We have virtual mass MAC, virtual damping coefficient CAC, and an activation force Fmin. So when the user applies a force, it has to exceed this Fmin value before it actually enters into the admittance control system. And we can select parameters. So for the virtual mass, we select it as the actual payload mass. Now this means that in the lateral plane, when the user pushes on it, it should feel like the mass of the payload. In the vertical sense, the system is carrying all the weight. So the user doesn't actually have to carry it in the vertical sense, but they just push it laterally. And then we can compute the damping coefficient based on an expected steady state force and steady state speeds as shown. The operation of the instrumented payload is shown here. And this is to say that admittance control isn't always enabled. It's only enabled after the system takes off and the operator is able to transition the system into admittance control before we push it along. And then at the end, we can, of course, land the system using a specific trajectory. Admittance control is also disabled according to the geofence boundary. So this was all performed in MAir, which is right behind us, which is an outdoor netted facility capable of motion capture and everything. And it has a very large area, but the tracking area of the camera is really only roughly 10 by 10 meters. And the very good safe tracking area is only about 6 by 6. Once we consider that we have this payload in this formation, this shrinks our area even further. And so we use this geofence boundary to make sure that when we're doing this complicated experiment, we're not going to lose motion capture data. We're not going to have it crashing, things like that. So we were able to show that once we have this 2 meter by 2 meter boundary, while you're inside it, everything behaves as normal. When you hit that boundary, we reject the input. The admittance controller does not allow the set point to go beyond it. And this actually acted as a cue to the user. So as the user pushed further, we tried to fight it because its set point wasn't. So that's another interesting thing that I'll discuss shortly. And then lastly, for our methods is the payload controller. We assumed a rigid formation. So RDPG, that's the payload position. We just add a fixed offset for each vehicle, assuming it's a rigid formation. And we do the feedback through the velocity command. So we're just doing a PI controller on the payload feedback such that the vehicles move in direction of decreasing error. So here are the results. What you're going to see in the top left is a user, first-person view of the user. In the bottom left, you can see the user about to approach the system. It has already taken off. At this point, the force estimate has just been zeroed, and we're about to enter admittance control. In the bottom left, there's going to be an overlay plot that's going to show a red dot with the set point of the payload in position, a dotted black circle that will show the activation threshold for the force, and a black arrow that's going to show what the estimate of the force is, as well as a geofence boundary on the outside. Once it reaches that geofence boundary, it's no longer going to accept input. So this is the first push. It moves. She lets go. It stabilizes. She does the second push as the black arrow goes beyond. It moves the system. It reaches the geofence boundary and rejects it. Here are plots from that run. So circles are when the force estimate was zeroed. X's are when the geofence boundary was hit. Stars are when the applied force receded or was released. So there was actually 2 applied forces, so there's 2 stars. If we notice in the very beginning, which was not pictured, the system took off and it was given time to settle. So that was to allow us to test the PI controller. So it was tuned very conservatively such that the user wouldn't accidentally push the system and it would jerk back some. So what actually is happening here is we allow the system to settle, the I term picks up, and it can reduce the error to actually go to its setting. At about 70 seconds, we zero the force estimate. So that's the user's about to approach the system. We say, okay, let's account for all this unmodeled error and zero the force estimate. At about 75 seconds, the user approaches the system and applies a force. This force exceeds the 2D norm. The 2D norm of the force exceeds the activation force threshold, which causes the admittance controller to update the set point in that direction. You can see that the controller also follows this and has a very small overshoot right around there, and the user releases it and it goes back to the set point. This happens again a few seconds later. The user applies another force, this time much larger. It exceeds the 2D norm. It makes the admittance controller change that set point and it moves forward. However, you can see with that X right there at about 85 seconds, it hits that geofence boundary. And now this user input is no longer updating the guidance. It's actually acting as a disturbance force because the system's rejecting it. And so there's a much larger overshoot at that point, which is just really, hey, like you've reached that point and you should no longer push anything. And so as soon as the user pulls back from that, the system is able to transition back to its set point. And so in conclusion for this work, this was the very first experimental validation of this kind of system. We're the first people to be crazy enough to do it. It's a user haptic guidance system where you can actually push on the payload so it goes in the direction you want it to go. And we were able to achieve this by having novel user-applied force estimation capabilities using inline tension sensors and haptic guidance with admittance control. The last chapter that I'll be discussing today is on deformable formation path planning in chapter 6. So going back to the UTM, the UAS traffic management application, we want to have multiple vehicles flying in the shared airspace. Formation flying has many benefits. One of them is it allows us to reduce the complexity of managing all this traffic because each formation can be treated as a single entity. Additionally, this allows us to maintain tighter communication between vehicles, and things like the Slung load project that actually requires you to maintain a formation. You literally cannot carry that Slung load if everyone's going in different directions. Now, those are some of the benefits. Some of the drawbacks of a formation are it's rigid, so you won't necessarily be able to move around obstacles easily. It's a little bit less flexible, for example, for smaller obstacles. So what we want to do is be able to plan paths for this type of system that leverages all these benefits while mitigating as many of these drawbacks as we can. In terms of general multi-vehicle planning and formation path planning, there's an abundance of. I'll be focusing on a few key areas. So in general, if we just had NV vehicles in an ND space, the planning dimensionality is N times NV because everybody can do anything that they want. And inter-agent collision checking is a function of the square of the number of vehicles because you have to check every pair to make sure they're not colliding with each other. Agent obstacle checking is also complicated where it's the number of obstacles times the number of vehicles. With a few vehicles, this is fine, but as the number of vehicles scales up, you really want to do something to address this complexity. I'm calling that first group of methods multi-SE2. This next one I'm going to be calling rigid. What you can do is do rigid formation path planning. So if you instead say, hey, all these vehicles are going to be in a rigid formation, and I'm just going to plan a path for them, this will reduce the problem complexity. And you can use cooperative control techniques to actually maintain those formations such that you can guarantee safety under certain conditions. And then you just plan paths for either the leaders, the formation centers, or the geometry of the formation itself, using standard planning algorithms as shown. Additionally, there's work on formation reconfiguration, such as in 16, where there's each of these specialized formations that are better for different scenarios. So perhaps that first one is really good for doing coverage patterns where they're able to go along in a group and move upwards. Maybe the wing pattern is good for communication or something else where they can have better drag that way. But each of these formations potentially can help in a different situation. And what you can do is, a priori, before you even do any planning, you can specifically plan between the formations such that you have an optimal plan to go between them. And then online, depending on the situation, you can switch between them. And so that has some values. But in the end, it's still just rigid formations that you're planning for, and you're just switching between them. Lastly, there's what I'm calling preliminary deformable path planning in 17, where at first we have waypoints that are selected by a user or via A-star. So you can see here the two options. And once you have those waypoints, this method uses particle swarm optimization to plan paths between the waypoints such that they minimize some cost function as well as satisfy constraints. And this is assuming continuum deformation as the formation control method. This shows some value, but it's not necessarily a general formation control. We want to have this more global, general method that can actually address that. And so our assumptions for our problem statement are, we have a static known environment, and for now we're assuming two-dimensional. We're constraining our planning space to a deformable formation. So what does that mean? In the top right, we're going to see this is the homogeneous transformation. So all the vehicles have starting position RIS and goal position RIHT for homogeneous transformation. And there's a Q matrix, which is deformation matrix, and translation vector D. And the goal is to plan for this through time, which can translate, rotate, scale, and steer through space. The planning dimensionality for this is no longer in terms of the number of vehicles, but it's in terms of the dimensionality. So for 2D, it's just these 6 parameters that you're planning for. And we're interested in success rate over a variety of runs, as well as total travel distance of all vehicles. Here you can see our approach. What we did is we decomposed this deformation matrix into a rotation, as well as to a scale and a shear. In the right side, you can see what different scales and shears look like for the formation. The top left is what the vehicles start in. One scale in X, one scale in Y, no shear. If we contract in both dimensions, we can get the top right. The bottom left is just contracting in the Y dimension. And finally, the bottom right is shearing as well as maintaining that initial scale. So you can see there's a wide variety of deformations that we can achieve. For obstacle formation collision checking, what we did is we first compute a convex hull approximation. So if you look in these images, each of these has a magenta convex hull on the outside, which is just a bounding triangle with the corners cut off to make it slightly more accurate. And then we use that bounding convex hull in standard collision checking algorithm. So every single time a collision check is required, we compute the convex hull, and we use it in collision checking. For inter-agent collision checking, we can leverage a safety theorem from continuum deformation. So the original theorem says if we have the eigenvalues of UD, which is the square root of Q transpose Q, as long as the eigenvalues are larger than this lambda min parameter, we can guarantee safety. This lambda min parameter is derived from the initial formation. So if you look at the distance between all the vehicles in the initial formation, it kind of tells you how much you can potentially scale and shear and whatnot from that. So really, delta G is the most that you expect the vehicles to move, and delta max is the most that they can move. So that gives you an idea of that. And as long as you satisfy that, you can guarantee inter-agent collision avoidance. Next, we can apply this to our decomposition of this deformation matrix. So because the rotation is only going to change the direction of the eigenvectors, and it won't change the eigenvalue magnitudes, we can assume it'll be 0 for now. Then we can compute UD squared, and if we take the eigenvalues of UD squared, it'll be compared against lambda min squared, such that we can do eigenvalue decomposition or calculate them and get a relation, an inequality in our state space variable. So now, if we just choose, if we sample a state space for our K, SX, SY, we can in constant time say, hey, if this is true, we're safe. If it's not true, we're not safe. So constant time inter-agent collision checking for this complex deformable formation. For testing and simulating this, we compared it against baseline. So as mentioned previously, we did the multi-SE2, which there's ND vehicles throughout space, as well as rigid planning, where the deformation matrix is just a rotation, as well as the translation vector not shown. And then 3 different variations of our method. So a 4-degree of freedom version where we just have one scale for both X and Y, a 5-degree of freedom where we have independent X and Y scaling, and finally the full method where we have shear as well. This was implemented in the Open Motion Planning Library, OMPL, where we added the new state spaces as well as collision checking as described earlier. And we use RRT star, which is a optimal planner, asymptotically optimal sampling-based planner for each of these methods. We did 1 second, 5 second, and 60-second time limits because RRT star will keep going until it finds a solution that is sufficient. And if it doesn't ever get there, it'll keep going forever. So we had to give time limits, and we tested on 3 representative environments as shown. So because what I'm showing here is all the 1 second time limit. 1 second is a little bit fast for the multi-SE2 because it's such a high dimensionality. it was unable to find it. The rigid method was able to find a solution, and you can see that it's just able to translate and rotate around the obstacles. The 4-degree freedom is also able to get around, and it's able to do a little bit of scaling to help plan a little bit of a shorter path. And finally, the 6-degree freedom does a little bit of everything to get through. For the medium environment, there is a narrow passage that requires the system to actually scale down. It cannot maintain that initial rigid formation. So the rigid is unable to finish. However, Multi-SC2 was able to find a solution. As you can see, all the vehicles go independently. And because it's only been 1 second, RT start isn't that optimal at this point. If we let it go forever, it would become very optimal. 4-degree of freedom, able to just very quickly scale down, get through and scale back up. Same thing with 6-degree of freedom. And finally, for the last environment, I'm calling this the impossible environment because there's no way that we can maintain a formation while going through this. The Multi-SC2 is the only one to be able to find a solution. So here are the results. What you're seeing is a table of both the success rate and the total distance traveled with the 1 second time limit. The rigid formation did all right with about 136 distance, but clearly the 4, 5, and 6 of our proposed methods are about pretty tightly bound right there as the best method. However, it's only the best method in scenarios where it could successfully maintain a formation, whereas the standard Multi-SC2 was able to find a solution in that impossible domain. And it's still effective even after 60 seconds. So even after 60 seconds, the Multi-SC2 for some reason could not find a solution for all of them. Out of 10 runs, it only had a subset to be able to find them. And you can see that the 3 methods kind of converge on that 120.1 for that medium case. So they're having fairly similar motions at the end. So in conclusion for this work, I propose a general deformable planner that has constant time inter-agent collision checking, as well as O of NO formation obstacle collision checking. It outperforms existing methods when formations are viable, but it does fail in cluttered environments. Future work could do some combinations to combine these to make it even better, but considering the UTM domain, there may not be a reasonable scenario to have cluttered environments for these vehicles to fly through. We may always want them to maintain a formation. And in conclusion for the dissertation, I was able to investigate 4 different multi-UAS missions. I presented 2 of them today, as well as some infrastructure details. And some of these open source contributions include the M330 Quadrotor, RC Pilot 826 Flight Controller, and Instrumented Payload. And I showed the very first experimental validation of user haptic guidance for multi-lift slung load, and presented a general and efficient deformable formation path planner. Here's a list of publications as a result of my dissertation. And future work, specifically for these open source contributions, we would love to have a larger platform to have some onboard sensing with these vehicles to really make this available to the entire robotics community such that you don't have to build it your own. You can kind of standardize this, have this low cost option. And within slung load, having a distributed computation and sensing setup, whereas instead of having an instrumented payload, we move those sensors to the vehicles, they share information between them, and we can actually make this a deployed system and actually work with, get it towards the end user. And this can be accomplished by doing some full-scale human subject experiments as well. And within formation planning, an obvious extension is to 3D, as well as incorporating some of this reforming or random initialization to make it more general. And just in general, I think that we've only scratched the surface of what we can do with multiple UAS. Our creativity is the only thing that's limited what we can do to benefit society. Thank you. And I would love to thank a lot of people. Robotics is definitely a team sport, and I could not have done any of this without everyone helping me. And so first and foremost, I'd love to thank my advisor, Ella Atkins, who's on this call. She has been extremely supportive throughout this entire journey, even when things got crazy, so I really appreciate your support. Thank you to my committee, Professors Panagu, Fazeli, and Roskofter. I really appreciate all of your support and feedback. Thank you to the A2 Sys Lab. You can see we've been having lots of fun for many years, flying in planes in. Thank you, Dina, for flying, as well as everyone that's helped me flight testing. It's really a really challenging thing to do, to have all these complicated multiple vehicles flying. It was an absolute endeavor, and this picture may have been at 5 in the morning, but we definitely earned that sushi lunch the next day. And everyone else, there's too many people to thank. There's so much. And thank you to the hackathon teams as well. Also, I want to play Where's Waldo with you guys for a second. Can you find all the places that Prince is located? Because Prince has been that one person that's truly helped me throughout my entire PhD, just showing up randomly and just making things work out of the blue. And I can't thank him enough. Thank you, Prince. And I would also love to thank my fiance Fa, who not only pushed my payload, but pushed me to do my best. Thanks to her mom Tanya, stepdad Ken, and my immediate family, my dad, my sister Mia, and my brother Joey. My dad's currently getting knee surgery. We just got out of knee surgery right now. So he recently retired. He's a printing press operator, worked his whole life. So I'm very thankful for all his hard work to get me to where I am today. Thank you.